I have a quote here from a textbook by Carl Logler in 1962, which I love to repeat, and I'd like to read it as best I can. The quote is, "Water is highway, byway, communications, medium, nursery, playground, school, room, bed, board, drink, toilet, and grave for a fish."
Water is a very different medium than air. Water is, just think of it as really thick. It takes a lot of energy to get a body through water.
I think what makes the oceanic environment so different than the terrestrial environment is that everything's in motion. If you imagine living a life where you were floating and where everything around you was kind of moving and floating around, it'd be a little disconcerting for us, I think. But that's the way it is in the ocean.
Since the earliest of times, the ocean has had a special allure for people everywhere. As a waterway that facilitates travel and commerce, a source of food, a place to escape searing temperatures. But above all else, the world ocean provides a home to countless marine plants and animals. A home that presents an extraordinary mixture of challenges and opportunities, quite distinct from anything on land.
One of the big differences between the marine environment and terrestrial environments is that when you're in the ocean, you're surrounded by water. And that's very different, being surrounded by a fluid, than being surrounded by air.
It's a very three-dimensional type of environment, the ocean is, whereas we kind of stay in a sort of horizontal plane in our terrestrial existence. We really don't get to move up and down in much of a three-dimensional sense. In terms of physical factors, of course, there's extremes in temperature. They tend not to be as extreme in the oceanic environment as in terrestrial environments.
Temperature is probably not as big a factor as most people would think. Most fish are poikilotherms, or cold-blooded organisms. That is, their body temperature is virtually the same as the water around them. Now, there are exceptions to that. Tunas, billfishes, and some sharks actually have heat retention mechanisms built into their circulatory and muscular systems that prevent warm blood from the muscles going to the gills to get cooled. But most fishes are the same temperature. So the way I presume this works is that the enzymes that these fishes use for their metabolism are adapted to the temperatures in which they live.
Nowhere is the capacity to adapt more important than near deep-sea hydrothermal vents, where temperature extremes are common.
The water's not incredibly hot down there. It's not the 400 degrees that some of the invertebrates are living in, but the surrounding waters are much, much warmer than the 4 degrees centigrade that you might get in the rest of the deep sea. But these fish have adapted to living in these hot waters. You've also got fish that are well adapted for living in extremely cold environments. For instance, there are fish that live in the Antarctic and in the Arctic waters. And they've adapted for their cold environments. And the way they do that is they actually put a form of ethylene glycol into their blood, antifreeze. The same as we put into our cars, they've got in their bloodstreams, and that keeps their blood from freezing up in these extremely cold environments.
While many fishes have the capacity to adapt to the temperature in which they find themselves, others apparently determine that it's simply easier to move as temperature changes occur.
Most fishermen know that fish tend to follow certain temperatures of water, and during periods of El Nino, we find billfish and barracuda, even as far north as Puget Sound up in the Seattle area, places where we would normally not see those types of animals at all.
It is also believed that temperature plays a key role in determining the depth at which marine organisms choose to live.
As you go deeper in the ocean, it gets very cold. The very deepest waters, the bottom waters, on average are about 2 degrees centigrade, perhaps even lower in polar regions. And so there's a whole different set of adaptations for organisms to survive in those types of environments.
But it's known that young stages tend to be surface dwellers and therefore live in warmer water, and as they get older they move deeper and deeper. If they're a water column species or a bottom species, there are species-specific patterns of depth utilization by these animals. We don't know if they choose them, or if they're just more comfortable there, or if they go someplace where it's too warm or too cold, they tend to metabolize too much or too little. But there are definitely depth-specific patterns by species of fishes in the ocean.
Ocean depth is important not only because of its impact on temperature, but also because, as depth increases, so too does pressure.
1 atmosphere of pressure is equivalent to 33 feet of water in the ocean. So every 33 feet, we're adding another atmosphere of pressure.
The organisms down in the deep sea have adapted to this. They do extremely well at this.
At one level, we can say that deep sea animals are adapted to their habitat because they have evolved enzyme systems that function well under high pressure, that wouldn't function well under low pressure. Another way that animals living in the deep sea are uniquely adapted to their habitat involves their ability to respire, to take up oxygen from the habitat.
Oxygen is required for aerobic metabolism, and fishes have a very tough job of extracting oxygen that's dissolved in seawater and having it go by their gills in a very efficient way, whereby there's a countercurrent exchange mechanism, and the gases in that water are diffused into the blood in the gills. It's a very tough job, and they pump a lot of water over their gills to do so.
Seawater contains only about 3% of the oxygen that air contains. So extracting oxygen from seawater is a big challenge to begin with. And if you go deep in the water column, the oxygen content drops off considerably.
Areas in which oxygen falls below about 1/2 millimeter per liter of water are known as oxygen minimum zones.
Oxygen minimum zones occur beneath areas of very high surface productivity, but this alone is not sufficient to create oxygen minimum zones. One needs a combination of high phytoplankton production, sluggish circulation, and oxygen-poor source waters all come together. We tend to find these along much of the eastern Pacific margin and through much of the Arabian Sea and Bengal Sea in the northern Indian Ocean. There's also a small, well-developed oxygen minimum zone off Namibia.
While oxygen minimum zones do present serious challenges, fishes that live in the deep sea have found ways to meet those challenges and survive.
Animals faced with life at very low oxygen levels have evolved some unusual morphologies. Very often there's a proliferation of surface area, and we'll find animals with all sorts of elaborate tentacles and branchiae develop to increase the surface exposed to the limited oxygen. Some animals will develop hemoglobin in their blood, which facilitates the oxygen uptake. Often we'll see clams, which normally are not red in other places, full of hemoglobin in low oxygen zones.
And they can scavenge oxygen. They can pull oxygen from the water, even when the oxygen content is extremely low.